Okay, here we are with chapter 14. We're looking at chemical periodicity. I never know if I pronounce that right, but that's how I'm going with it. So what this chapter is about is kind of a deep delve into some of the trends on the periodic table. And so you'll see with a lot of examples, we want to be referencing the periodic table, and you might even want to have one that you can take notes on for a lot of the pieces we're going to look at. So the first things we're going to look at is what does an atom's electron configuration have to do with the periodic table? Turns out that there is a really neat way to find the electron configuration of an element using only the periodic table. And that's what we're going to do moving forward from here, is that no more of those electron filling Aufbau diagram things. No, 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 no. We can do all of that just with a periodic table. Now, the reason we can do this is because of all the subatomic particles in an atom, it's really the electrons that play the greatest role in determining the properties of what we're dealing with. And one of the things that we're going to see is that, and we've talked a little bit about earlier, is that the arrangements of elements on the periodic table depends on those properties. So, let's kind of back this up a moment. Electrons determine properties. Properties determine how the periodic table is formed. Therefore, the arrangement of the periodic table depends upon the electrons. And we'll see it's a very deep relationship. Now, just on a kind of broad strokes, we're going to see that elements can be categorized into 4 different categories according to what is going on in their electron configuration. First are the noble gases. So with the noble gases, what we find is that their outermost S and P sublevels are completely filled. Now, as a note, in the case of something like helium, helium's electron configuration is 1s2. In the first energy level, which is its outermost energy level, there only has 2 electrons total. So, and in the first energy level, there's only the S. So by saying the S and the P are filled, that's still okay. So again, we see there helium 1s2, we see neon 1s2, 2s2, 2p6. So once again, looking at this, the second energy level is the highest, 2s2, 2p6. That's a filled outermost. Argon, and the third energy level is the highest. So again, 3s2, 3p6. Krypton, 4s2, 4p6. And we could just keep looking at this way. If I was to look at xenon, what would we expect it to end with? That's right, 5s2, 5p6. Next is the representative elements, and this is what most of the other elements are, and it's going to be the muddiest of all. So with these, they're going to have a partially S or P sublevel filled. So partially filled. So again, only a partially filled S or P sublevel. And again, there's 3 groups that have special names. Group 1A is the alkali metals, 2A is the alkaline earth metals, 7A are called the halogens. We learned that back in chapter 5. And here's the neat thing. For any of the representative elements, its group number will be equal to the number of electrons in its outermost energy level. That means its valence electrons, which we'll talk more about coming up. So again, like the alkali metals, in their highest energy level, because they're group 1A, they would have 1 electron in their highest energy level. All the alkaline earth metals, because they're in group 2A, have 2 electrons in their highest energy level. The halogens, group 7A, because they're group 7A, that means they have 7 electrons in their highest energy level. So we can see here just as an example, so group 1A, the alkali metals, because it's group 1A, only 1 electron in its highest energy level. So if you look at lithium here, the 2 is its highest energy level, and it has 1 electron in its 2s. Sodium, the third energy level is the highest, and it has 1 electron in its highest, the 3s. Now, carries on, group 4A. So because group 4A, we would expect 4 valence electrons, or 4 electrons in its highest energy level. So if we look at carbon, its highest energy level is the second, so that means the 2s and the 2p there make up its highest energy level, and we can see there's 4 electrons there. Or a silicon, again, the third, now it's going to be the third energy level, 3s and the 3p, 2 electrons. Transition metals continue to be weird. Transition metals are electrons at their outermost S sublevel should be filled. And we're now filling up the nearby D sublevel. So again, they're going to have some in their S, hopefully filled, but again, transition metals are weird, and some now in the Ds. The inner transition metals are going to be very similar, but instead of S and D, it's S. Okay, so here's where the power comes in. We're going to break the periodic table up into blocks. And if an element is in a block, that tells us which sublevel is being filled in last. So if there's an element in the P block, that means that a something P sublevel is being filled in last for that element. And this is how this is going to work. Kind of a few steps in. I'm going to walk through this with you with a periodic table. You're going to find the element you want, figure out which block it's in, determine which period it's in, and we're going to see that there's a reason for that, and then count how many elements into the block it is, and that's going to tell us how many electrons are in that sublevel. So this is our periodic table in terms of blocks. So kind of looking at this, so here, groups 1A and 2A with helium here in the corner make up the S block. The P block is over here, so group 4A through 8A make up the P block. Then we have the D block, the transition metals. And finally the F block, the inner transition metals, those weird guys down at the bottom. Now, here's how this is going to work. Notice that for the S and the P's, so the S and the P's, that they kind of go down in scaling. So if we start from the top, so first period 1S, second period 2S, third period 3S, fourth period 4S. That's because for the S and the P blocks, the highest energy level can be seen from just the period. So if we're in the fifth period, that means that in, let's say, the fifth period and we're in the S block, that means we're in the 5S sublevel. Same thing with the 5P. If we're in the P block and we're in the fifth period, so we're something like iodine, let's say. Iodine is down here, it's a halogen, it's in the fifth period, it's in the P block. That means that its highest sublevel would be a 5P. Now for the D block, it's a little bit different. For the D block, the energy level that we deal with for the D is going to be the period minus 1. So you can see the 3D is actually in the fourth period. The 4D is in the fifth, so on and so forth. The F block, very similar, but it's the period minus 2. And the F block kind of fits in right after the 6S and the 7S sublevel. Okay, we're going to walk through an example. I recommend as I do this that you grab a periodic table. Please pause this as necessary. To do so, it'll be much more helpful for you to have a periodic table out in front of you as I go through this. So our first example is going to be nitrogen. So we find nitrogen on the periodic table, and we know that nitrogen is in the P block. So what that tells me is if I'm writing out the electron configuration for nitrogen, it's ending with something P. Something P. Next, nitrogen is in the second period. That tells me that nitrogen, that P that I'm filling in is actually the 2P. If it was in the third period, it'd be 3P. If it was in the fifth period, it'd be 5P. But it's in the second period, so it's going to be 2P. Next, nitrogen is the third element in its block. So we start counting from the left. Boron's the first, then carbon, then nitrogen. Because it's the third element in, that means there are 3 electrons in the 2p sublevel. Now, bringing this all together, you now just have to backtrack this. And you could either run it backwards. So, okay, we've now filled in the 2p. So what comes before the 2p? Well, the 2s. And to get to the 2p, how many electrons do you need to go in there? Well, you need 2. So you can backtrack it and just fill in everything prior to that. Okay, so we're going to do another example here. We're going to do nickel. Um, so the first thing we do is we identify nickel on the periodic table, and that's it right there. So, again, kind of figuring out where it ends, we go, okay, which block are we in? Well, this would be the D block. And now which energy level is it in? Well, we see first energy level, then second, then third, then fourth. Now remember, because we're in the D block, that the energy level of its ending isn't the period, it's the period minus 1. Since it's the fourth period, that means we are in the 3D. Now the D block, again, starting kind of here with scandium and going to here, we want to count how many in Nicholas. So 1, 2, 3, 4, 5, 6, 7, 8. So nickel is the 8th element in, so it ends in 3D8. Now, if you wanted to write out this whole thing, you have a few options. This is actually really where the abbreviated configurations really come in handy. So remember, to do an abbreviated configuration, you look for the noble gas that comes before your element, which would be argon here. So in brackets, I would write AR. And now we need to figure out what goes between argon and this 3D sublevel. So that would be this stuff right here. That's between argon and our target. So we just fill that in. So same thing. Which block is it in? Well, that's in the S block. Which period is it in? 1, 2, 3, 4. So 4S. And how many in? Well, 2. So there's the electron configuration for nickel. So the next example we're going to do, and our last example, will be iodine. So again, we find our element of interest. So I find iodine right there. And again, the first thing I ask is, what block is this in? Well, that is in the P block. Again, the P block being from here to the end of the periodic table. Then we count how many in we are. So 1, 2, 3, 4, 5. So we're something P5. Now remember, for the S and the P block, the energy level is just equal to the period. So 1, 2, 3, 4, 5. So we're ending in 5P5. And again, I think this is really where the abbreviated comes into play. So I find the noble gas that comes before it. That's krypton. So in brackets, I put Kr. And then I have to kind of fill up to the 5P, which would be kind of all of this mess through there. So we kind of go one at a time. So here's that first chunk on our journey. And again, we ask ourselves, well, what is that? Well, that's the S block, and that is the 1, 2, 3, 4, 5. So 5S. And how many did I have to travel through? That's 2, so 5S2. And then next, I'm in the D block. But remember, the D block, the energy level is the period minus 1, so it's not the 5th energy level, it's the 4th, 4D, and we count over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 40, 10. And that is the electron configuration of iodine. So now we're looking at periodic trends, and as we go through this, there's a few pieces of information with each trend that you need to focus on. So you need to be able to recognize on the periodic table kind of how these trends change. So that means as we move to the right on the periodic table, are we increasing in this factor? Are we decreasing? As we move up, are we increasing or are we decreasing? So not only know what the trend is, but being able to explain it. That's going to be a critical part of this. So, first atomic trend or periodic trend we're going to look at is atomic size or atomic radius. And although atoms don't actually have rigid borders because they have that kind of fuzzy cloud model where the electrons are, we can still estimate the relative size of atoms based upon how they bond, and specifically how close the atoms get together when they bond, so we can kind of pretend that they have a stable radius. And so that's what we can find. So the group trend, so again, groups being up and down, the group trend. So atomic size tends to increase as we move down. So again, as we move down the periodic table, atoms get larger. And this is because as we're going down, if you remember from the last section, we start adding more and more energy levels. And as you add more energy levels, you add layers. My terrible joke that I always tell is that atoms are like ogres. They have layers. And the more layers you have, the bigger it is. Now the periodic trends here, that's the side to side, generally atoms are going to get smaller as we move from left to right, which is a little counterintuitive because as we move to the right, they actually get more massive. And this is because what we're doing is we're adding more protons and electrons, but we're not adding more energy levels. And remember, protons having a positive charge and electrons having a negative charge attract each other. And it's really that we're adding more protons is the big piece here. So we're adding more protons so the nucleus has a more positive charge. So those electrons that are around it are going to be more attracted to it. And as we all know, the more attracted you are to something, the closer to it you get. Unless you're a stalker. Then you keep a safe distance. So looking at the periodic table, a great question would be, and what we could see on the opportunity, which element would have the largest atoms? So first thing we're going to do is track down our atoms here. So I see we have lithium, we have beryllium, we have sodium, and we have magnesium. So we're kind of in this little corner here. Now, which atom to be the largest? So what we remember, atoms get larger as we move down, and atoms get larger as we move to the left. So we ask ourselves which atom is most down and left. And the answer to that, unsurprisingly, by looking at this, is sodium. So sodium would be our winner there for the largest atom. Next is something called ionization energy. So what ionization energy is, it's the amount of energy needed to remove an electron when an atom is in its gaseous state. And this just gives a nice standardization of this. So we're not concerned with we're adding energy and causing things to melt, we're adding energy, we're causing things to boil. We're assuming you're already a gas, and it's the amount of energy needed to remove one electron from that atom. Now, what's important is that there's different ionization energies. There's the first ionization energy, second ionization energy, third ionization energy, so on and so forth. The first ionization energy is the energy needed to remove one electron when you've removed nothing else. The second ionization energy refers to removing a second electron after you've already removed the first. So if you're looking at the second ionization energy, you're saying this is how much energy it costs to remove a second electron after you've already paid the cost of the first ionization energy to remove the first electron, and so on and so on and so forth. So if you were looking at, let's say, the fourth ionization energy, we could ask ourselves, well, how many electrons have we already removed? And the answer would be 3. We're paying to remove the fourth. And our trends here. So group trends, again, that being up and down. So as we move down a group, ionization energy goes down. So that means it becomes easier. And the basic idea behind this is that atoms are larger. So remember, as we move down, atoms get larger, they have more energy levels. And as the atoms are larger, there's less attraction between those positive and negative charges. So it's just easier to remove. And again, less attraction, easier to remove. Now the periodic trend, so as we go from left to right, ionization energy goes up. Why does it go up? Well, because again, as we move from left to right, atoms get smaller. That means the electrons are closer to the nucleus, and the closer things are to the nucleus, the more attracted they are. And the more attracted they are, the harder they are to remove. So, like the last example, we have our periodic table here. Which element should have the lowest ionization energy? So we're looking at the lowest ionization energy. So again, we remember our trend as we go. So again, to focus on low, we want to go down. ionization energy decreases as we go down, and it's going to decrease as we go to the left. So again, we see hydrogen, helium, francium, and radon. So which of those is the most down and to the left? And the answer to that would be francium here. And because it's the most down to the left, it has the lowest ionization energy. Next trend we're going to look at is ion size. And ion size is weird. So one thing you have to remember is what we're talking about with ions. So when we have a metal, and metals form ions, they always form cations. That means that they are positive. And to become a positive ion, that means they have to have lost electrons. So a positive ion, because it's lost electrons, will always be smaller than the parent atom. And one way that you can really think about this, I have one statement on there, and yes, the electrons, because electrons do repel each other, you have less electrons, less repulsion, but you've also just removed an entire outer layer of the atom. You've removed all the electrons in their outermost energy level. Because of that, you've removed a layer. Think of it like peeling an onion. When you take a layer away, the onion gets smaller. However, the opposite of this, so anions, remember, anions gain electrons. Anions are going to be larger than their original atom. And that's because you're now sticking more electrons into roughly a very similar area. And electrons, all having a negative charge, repel each other. Two negative charges repel. So again, more electrons, more repulsion, bigger ion. Now, what does this have to do with the periodic table? Well, going from left to right, we do see a decrease in size while we're still in the metal. So while we're in the positive ions, we get smaller, 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 because the atoms are getting smaller, smaller, and smaller. But when you hit group 4A, you see this jump in size, because now we're talking the anions. So now we're talking nonmetals. So we get this big jump in size, and then it's going to slowly decrease again because their atoms get smaller. And as you move down a group, ions get bigger, just like with the atomic radius. And here's kind of a slide illustrating this. So if we look in group, so think of like period 2. So here's lithium, then beryllium, we get smaller. Boron, we get smaller. But when we get to the nonmetals, we see this jump up in size, and then we get a little smaller. Again, we look to the next group, we see something very similar. Start at the left, small, a little bit smaller, a little bit smaller, big jump, and then a little bit smaller. And again, the colored, just a way to read this, the color here, a colored sphere or half sphere is the ion, the gray is the regular. So again, you can also see that for your metals here, the ion, the pink, is always going to be smaller than the parent atom. But for the nonmetals, the blue, the ion, is always going to be larger than the original. So we're almost done. We have electronegativity. So what electronegativity is, and this is going to become very important as we move on to future chapters. It is how attracted an atom is, more specifically its nucleus, but how attracted an atom is to electrons when they're in a chemical bond. So we have a chemical bond, and it's how attracted an atom is to the electrons that are in that bond. And again, very, very important as we move forward. Now, as we move left to right, electronegativity goes up. And again, this all goes back to size. So as we move from left to right, atoms are smaller. Because they're smaller, those electrons in the bond are going to be closer to its nucleus than if it was large. But so again, they're small, so the closer the electrons, the more attracted they are. More attraction means greater electronegativity. As you move down a group, electronegativity goes down. And again, as atoms get larger, the electrons in a bond are going to be farther from the nucleus. The farther they are from the nucleus, the less attracted they are. So less attraction, less electronegativity. So, which of the following will have the highest electronegativity? So again, electronegativity increases as we move to the right, because we're getting smaller, and it increases as we move up, getting smaller. So let's look at our options here. So we have fluorine, we have neon, we have oxygen, and we have chlorine. Now again, it's going to increase as we go up and right. So it's really tempting, really tempting to say that, hey, answer would clearly be neon. But there's a trick here. Neon's a noble gas. What's special about the noble gases? Well, remember, noble gases don't tend to form chemical bonds. They don't tend to react. Because of that, we normally don't talk about noble gases having an electronegativity value. Because again, they don't form bonds, so they don't have an attraction to electrons in bonds for the most part. So we tend to ignore the noble gases when we are talking electronegativity. So that would leave fluorine being the most up and right. And here's just a summary of the trends in total. Doesn't explain why they are, but just gives the basic trends that you need to know.